this about 2 weeks ago. So the talk, the problem is the following. So if I have a regular surface, smooth or analytic, in the Euclidean space or in the Minkowski space R31 with an umbilic point at the point P0. So I have a surface with an umbilic point at P0. So the question is, what is the maximum number of stable umbilic points P0 can split up into under deformation of the surface? So what does it mean? This means that if I have a surface M equal to M0, and I take a family of surfaces M of t, with t a parameter in some space, Rn, close to 0, t close to 0, the question is, what is the maximum number of umbilic points the surface MT has near P0? So if this number is finite, and it exists, we call it the multiplicity of the umbilic point. So what we are going to do this talk is about defining this number and calculating it at umbilic points that are not that are stable and not stable. So the structure of the talk is the following. First, I'll start from the basics and define what an umbilic point is on a surface in R3 or in the Euclidean space R3 or the Minkowski space R31. Then define the multiplicity of the umbilic point and state some of its properties. Then we'll give some applications, and finally relate the multiplicity of an umbilic point to the multiplicity of the equation. This is a notion Bruce and I defined a while ago. If you have some differential equation, binary differential equation, then you can define its multiplicity. And it happens that there is a relation between the multiplicity of the umbilic point and the multiplicity of the differential equation of the lines of principal curvature. So let's start with umbilic points first on surfaces in the Euclidean space. So let's take phi, a local parametrization of my surface, and n, the Gauss map of the piece of M given by the image of phi. So I don't care really if M is orientable or not, but locally it is, and I can take the Gauss map as given by the vector product of phi of u, the derivative of v with respect to u, times phi with respect to v over the norm. Recall that here we are in the Euclidean space, so I can do that without any problem. So once we have the Gauss map, or before the Gauss map, we have the first fundamental form, which is the induced Riemann metric on the surface induced by the Euclidean metric, and it has coefficients E, F, G. This is, as I said, just the elementary course on differential geometry. So then with the Gauss map, we have the Weingarten map, and it gives us the second fundamental form. The second fundamental form is a quadratic form, and it has coefficients L, M, N, given by the scalar product of N, the second derivative here of phi with respect to UU. M is N scalar with the scalar inner product with phi, the second derivative of phi with EV, U and V, and N is the scalar product of N with phi, V, UU. So what is an umbilic point? So we have, suppose I have a surface, I have my surface N and the point P0, I fix my point, the point P on the surface. At this point, I have, suppose I choose a direction in the tangent plane. So I have, with this direction and the normal to the surface, I can form a plane which passes through P and which is generated by N and V. So this plane cuts the surface on along a curve, and this curve is a plane curve, has a curvature. We call the curvature of that curve the normal curvature of the surface along V, and which is given by basically by the second fundamental form along V. here, this curvature, in fact, of this curve does not depend on the choice of curve. It depends only on this direction. So this is the normal curvature, varying v on a circle, unit circle in the tangent plane. Because it's a continuous map, it will have a maximum and a minimum. And the maximum and minimum are attained along two directions. This maximum and minimum are called the principal curvatures. And a point is an umbilic point if and only if a point is an umbilic point when the principal curvatures are equal. Okay? And the directions along which we have a principal curvature are called the principal directions, and their integral curves. So at each point away from the umbilic point, we have two principal directions, which are orthogonal, and the integral curves of these principal directions are the lines of principal curvature. As I said, this is a crash course on differential geometry of surfaces in R3. So the equations of the line of this principal curvature, at each point we have two away from umbilic points. At umbilic points, every direction, because K1 is equal to K2, every direction is principal. And these lines of principal curvatures are the solution of this equation, which can be written, it's a differential equation, a binary differential equation, which can be written in a simple way as a determinant. Okay, it happens, these equations are studied for a long time. At each point away from an umbilic point, I have two principal directions, two curves, basically. Away from umbilic points, I have two directions. One is blue, one is red, and the other is blue. Just to separate them, I put two colors. So one is blue, and the other is red. And you integrate these directions, you get the lines of principal curvature. And at umbilic points, you have this generic configuration. This is called the lemon. This is the star. And this is the monster. It has nothing to do with the Loch Ness monster. This is the monster of the lines of principal curvatures on surfaces in R3. So if you write this determinant in a nice way, you get the binary differential equation of the line of principal curvature. So this is just this equation, the determinant. You expand this determinant and you get this binary differential equation, which means that each point, when the coefficients are non-zero, you get two directions and you integrate them, you get the lines of principal curvature. We denote these coefficients, will play a role soon. With us, we give them a notation. We call this A, B, and C. In all the talk, A, B, and C will be the curly A, curly B, curly C, will be the coefficients of the equation of the line of principal curvatures. Of course, they depend smoothly or analytically on the parameters U and V. So there is an observation that a point is an umbilic point if and only if all the coefficients A, B, and C are equal to 0 at that point Q, which gives my parabolic point. So when you look at this equation to get an umbilic point, you set this to be 0, you solve your system, and you get your umbilic points. Okay. All right. Now let's go back to surfaces in the Minkowski 3 space. In the Minkowski 3 space, we have this pseudo-scalar product. So if you take two vectors in R3, here x and y are vectors in R3, but with the pseudo-scalar product, you don't have plus, you have a minus here, which means what? You get a cone in R3, and any direction on this cone, if I take any vector on this cone, any vector x on this cone, I have x is equal to 0. So in the Minkowski space, you have to be careful with these points, with these vectors, which are called like, which have a norm equal to 0, and points inside this cone, or vectors inside these cones, have scalar product negative. For example, if you take x1, x2 equal to 0, and you take x, you will get minus x3 cubed. So x is negative. This is called a time-like vector. And vectors outside these cones have positive norm, and they are called space-like. Okay, so this is the key difference with the Euclidean space. So if we take a surface, we take surface in R31 here. We take a surface in the Minkowski space, parameterized locally by a map phi. We can have points. The problem here with our surface, we can have points where the induced metric is degenerate. So if we have our tangent cone, I can have a surface here where the tangent space is tangent to the cone. If the tangent space is tangent to the cone, then the metric here, the induced metric, is degenerate. It means what? That means that the vector product of phi of u with phi of v is 0. So the usual normal vector has norm equal to 0, is like. So because of that, we cannot define the Gauss map. The Gauss map is not defined at these points on the LD. Okay, but for our purpose, what are we trying to do? We're trying to get the equations of the lines of curvature. As we saw, the Gauss map is well defined here, away from point on the LD. So if I have my surface, this is just my surface, and this is these points where the metric is degenerate. In general, on one side, I have a Riemannian, the metric will be Riemannian, on the other, it will be Lorentzian. At each point here on this Riemannian or Lorentzian region, the Gauss map is well defined. The problem, it's not well defined here. So how do I define the lines of principal curvature? So what we do, we go back to the equation of the lines of principal curvature. We know that they define our problem is the denominator here, which has the norm 0. So what we do, we define L bar, which is, we just get rid of the denominator. We call the L bar here is phi of u scalar vector product with phi of v, scalar phi of u, and define in the same way m bar and n bar. In this way, because the lines of principal curvature are homogeneous in L, M, and N, so I can just multiply by the original lines of curvatures. I have L, M, and here L, M, and N, and L. But what is L? L is phi of u, phi of v over the norm, phi of v, phi uu. So what I do, I multiply this equation by multiply all this equation that has L and M by the norm of phi of u, phi of v, and then you get rid of the denominator. What you get here n bar, n bar, n bar, L bar. And what does it give you? It means away from where phi of u times phi of v is different from 0. So which means on the Riemannian or Lorentzian part, this equation is exactly the equations of the line of curvature, the line of principal curvature. So this equation, in fact, extends the lines of principal curvature through the locus of degeneracy of the metric. Okay, so this is a more general equation of the line of principal curvature on surfaces in R31, which agrees with the lines of principal curvatures, away from this locus of degeneracy. Then this allows us to define umbilic points. This gives umbilic points at like points. So we say that the point is an umbilic if the coefficients, these coefficients of the extended lines of principal curvature are 0. And in particular, we say that an umbilic is space-like. So as I say, we have the LD here, the LD. We are on the Riemannian part, we say the umbilic is space-like. On the Lorentzian part, we say the umbilic is time-like. And if the umbilic happens on the LD, then we say that it is a light-like umbilic point. Okay. So there is on our surface, there is a curve that I said before, which is called the locus of degeneracy of the metric. But there is also another curve, which is the discriminant of this equation. The discriminant means the locus of points where the two directions defined by this equation coincide. And in the Lorentzian region, we call this discriminant the light-like principal locus. Why is it called light-like principal locus? Because in the Lorentzian region, we have at points where there are two solutions, one is space-like and one is time-like. They are orthogonal, pseudo-orthogonal, and the one is space-like and one is light-like. And when they come together, they become light-like. And they come together along this curve, which is the discriminant of the equation. It is called the light-like principal locus. So what is the configuration of the lines of principal curvature along the light-like principal locus? So away from the umbilic points, the lines of principal curvature in the time-like region are in general on this way, one of these possibility families of cusp. This is called folded saddle. And this is folded node. And this is folded focus. I'll come back to these notations later on. Okay. And at points where the LPL meets the locus of degeneracy, they meet the locus of degeneracy here is drawn in thick. It's in fact a principal curvature, a line of principal extended curvature. So the locus of degeneracy is a solution of our equation. As you see here, it changes color as it touches the LPL. And you have this configuration of the lines of principal curvature at points where the LPL is tangent to the LD. So here we have a Riemannian region. Here we have a Lorentzian region. At umbilic points, if the umbilic is space-like, when we have the same configuration as in the case of surfaces in the Euclidean space. At time-like umbilic points, we have 5 possible configurations. And what's happening here is that the discriminant of my equation is equivalent by changes of coordinates in the source to, it has a more singularity of, it's equivalent to this function, plus or minus v squared, here plus or minus, yeah. And the discriminant here has a more singularity, but with index 1, index 0 or 2, here index 1. So the umbilic points, at umbilic points, the discriminant has a more singularity, or it has what's called in singularity theory A1 plus or minus singularity, generically at generic points. And the time-like umbilic, space-like umbilic points, it's an A1 plus, and at time-like umbilic points, it's an A1 minus. Okay, so this is the first part of the about umbilic points, but I cannot resist doing a bit of publicity to some work I published in 2013 about the Karakteri-Odori conjecture. It happens that for regular closed and convex surfaces in the space, in the Minkowski space, of class C3, any such surface has at least 2 umbilic points. So this is true, but the problem is still open when the surface is in the Euclidean space, okay? But for the surfaces in R3, one in the Minkowski space, any closed one, which is convex and regular of class C3 has at least 2 umbilic points. So let's start now at the main point. Main point of this talk is how to count the umbilic points. To count the umbilic points concentrated on a degenerate umbilic, we need to get the equations of the umbilic points. So I'll start with some elementary observations. So before that, from now on, we take our surface in the Minkowski space. Why? Because umbilic points on surfaces in R3, they behave exactly like space-like umbilic points on surfaces in Minkowski space. So I just deal with the surfaces in Minkowski space, but all the results work also for surfaces in the Euclidean space. We also assume that our surface is analytic. For simplification, the results are valid for smooth surfaces, but I need to put some hypothesis. So let's start with this elementary lemma. If I have a surface with an umbilic point, if the coefficient E of the first fundamental form is non-zero, then if the coefficients of the equations of the lines of curvature, remember umbilic points are where the coefficients A, B, C of the equation of the line of principal curvatures are 0. So if E is different from 0, then the vanishing of B and C implies the vanishing of A. Similarly, if F is different from 0, then the vanishing of A and C implies the vanishing of B. If G is different from 0, then the vanishing of A and B implies the vanishing of C. And fact is, if I have a regular surface in R3 or R3-1, then the coefficients of the first fundamental form, E, F, and G cannot all vanish at the umbilic point. If they cannot all vanish at the umbilic point, then one of this situation is true. If one of this situation is true, then it means that I don't need 3 conditions to check that the point is umbilic. To check that the point is umbilic, I go here. If, for example, E is 0, and then the point is umbilic if and only if B equal to 0 and C equal to 0. Then the consequence of this elementary lemma is umbilic points are given by the vanishing of 2 functions. And this is vital. Why? Because by vanishing of the A and B and C are functions in 2 variables. If they are given, if the umbilic points are given by vanishing of 2 functions, then I can count them. Well, I'll tell you in a minute how I can count them, but before then, let's define the multiplicity of umbilic points. So I have a regular surface, and P is an umbilic point, and the multiplicity, we define the multiplicity of the umbilic point, and we denote it by mu of P as the maximum number of umbilic points it can split up into and the deformation of the surface. Now, a little bit of algebra. If I denote commutative algebra by O2, the ring of germs of holomorphic functions from C2 to C, and if I take H and K two such germs, we denote the ideal, the codimension of the ideal generated by this function hk by m of hk. So the multiplicity of the ideal is just the dimension of this complex vector space O2 over H over the ideal hk, okay? And we know from Arnold, from the book of Arnold, Gusenzadeh, and Varchenko, that this multiplicity of the ideal, what it does, in fact, it counts the number of roots of the system. So I have a system of my equations, h of 0, k of 0. This multiplicity will give me the number of roots of the system h of t, k of t, where h and k of t are deformation of h0, k0. And you can see where we're getting there. Now, for the multiplicity of umbilic, because the umbilic points are given by the vanishing of two functions, then if I have non-analytic functions, an analytic surface in R3 and P is an umbilic point, then our multiplicity of the umbilic point is just the multiplicity of the ideal generated by the function B of C. Why? The multiplicity of the umbilic point is the number of solutions it can deform after deformation of the surface. But the umbilic points, when E is different from 0, are given by the zeros of these equations. So this, the number it can split up into, is exactly the multiplicity of this ideal. And similarly for F and G. What here, B and C denote the complexification of the real analytic counterparts of this, because we take analytic because I can complexify the coefficients of the equation, okay? So we have then a way of counting our the multiplicity of our umbilic points, and it's important to say why we define as the maximum number. We defined here as the maximum number because the multiplicity is. Why did we define our multiplicity as the maximum number of it can split up into? Because our surface is in the real. And this multiplicity is complex. So sometimes in the real case, you don't have if you have it's the usual problem, you have a polynomial. In the complex case, it has n roots. In the real case, a polynomial of degree n, it has always n complex roots, but in the real case, it has at most n roots. So here, this multiplicity is given by this number, but it's the maximum number of the umbilic point that can appear on the surface. So I'm just going now that we defined the multiplicity of umbilic points and we know how to count them. Now I'm going to give some results. First of the umbilic point of multiplicity 1. So if I have a space-like or time-like umbilic point, then the multiplicity of my umbilic is 1 if and only if the discriminant of the BDE has a more singularity. So in the case of space-like, it will have singularity A1 plus. In this case of time-like, the LPL will have singularity of type A1 minus, and the multiplicity is 1 if and only if the singularity is most. Now, at like umbilic points, the multiplicity is also 1 if and only if the LD has more singularity. So what you do here, it can have the LD, the locus of degeneracy of the metric, can have multiplicity, can have singularity A1 plus or A1 minus. Now there is this theorem about deformation of surfaces. If I have a surface with a degenerate umbilic, then I can find a one-parameter family of analytic surfaces, MT, with M equal to M0, such that all the umbilic points of MT near P0 have multiplicity 1 for T small enough. The proof here goes to the jet space. You look at the jet space, you stratify it, and you can show that we can construct this family that avoids, when you deform it, it avoids the strata of multiplicity greater than 1. How about umbilics of multiplicity greater than 1? So we relate here the umbilic points of multiplicity greater than 1 to the singularities. You remember when the multiplicity of P is 1, we related to delta has an A1 singularity. The discriminant has an A1 singularity. All the LD has an A1 singularity when it's light. So what's happened when the multiplicity is greater than 1? Then if the umbilic is like, then under some conditions, we suppose if the singularity of the locus of degenerate of the metric is equivalent to a quasi-homogeneous singularity, then the multiplicity is exactly the Milnor number of the singularity. So if the f u of v equal to 0 gives this locus of degeneracy of the metric, if f equal to is the LD, what is the Milnor number? Milnor number is just the dimension of O2 over the Jacobian ideal. And this, in the case of quasi-homogeneous, this is exactly the multiplicity of the umbilic point. Okay. Now for space-like or time-like umbilic points, if the discriminant has a simple singularity, it happens when in a space-like case, because the singularities are always isolated points, the curve delta equal to 0 is an isolated point. So the simple singularities are of type AK2 minus 2k plus 1. So it's equivalent basically to V 2k plus 2. It's equivalent to this normal form of the singularity, this one. Then the multiplicity, is equal to k. And if the time-like umbilic point and it has a simple singularity, then we have this simple singularity does this multiplicity. So why I'm doing this? Because we have a consequence. As you can see, the light-like umbilic points I can get if in the light-like case, if I have quasi-homogeneous and the Milnor number is k, then the multiplicity is k. Here, if I have a singularity with of type A to k minus plus 1, then the multiplicity is k, and the same here. So the question is, if I give you any integer, is there a space-like, time-like, or light-like umbilic point which has multiplicity k? And the answer is yes. So what we do, we go back to the previous examples, the previous cases, and construct examples of a surface with a light-like degenerate locus that has Milnor number k, or a surface with space-like or time-like umbilic point with a simple singularity of the discriminant, and we can construct any type of this. We can construct any type of the singularities that I put here, which means that if you give me any k, I can give you a surface with an umbilic point. You can choose what type of umbilic point, and it has multiplicity k. Okay. So let's now go to some applications. The applications is on bifurcations of codimension 1 umbilic points. Here, I'm going to restrict to surfaces in R3 or space-like umbilic points on surfaces in R3-1, simply because the bifurcations of umbilic points, time-like umbilic points or light-like umbilic points have not been studied yet. So they are yet to be studied. So what we do here is we just go to the literature, get the cases that have been studied, and look at their multiplicities. So if I look at the codimension 1 umbilic points and the way they're bifurcated are studied by Gutierrez, Sotomayor, and Ronaldo Garcia, which I hope is here. And there are basically two generic types of umbilic of codimension 1, which the authors here denoted by D12. And what's happening in D12? You have a change from a lemon to a monster. So basically, there is no creation of umbilic here. You just have a change from one to another. So in the deformed surface, you just have one umbilic which changes type. So in the number of umbilic here should not change. In D1 to 3, what you have a star and the more star that joins together and then go to nothing. So in fact, at this umbilic point, the multiplicity should be 2, no? And this umbilic point, the multiplicity should be 1. This is what the bifurcation tells us. And in fact, going to the work of Gutierrez, Sotomayor, Garcia, and getting the simplified form of the equation of the lines of principal curvature, and just calculating the ideals, the codimension of those ideals, we find that the multiplicity of MUD1, 2 and MUD1 to 3 is exactly 1 and 2, which is confirmed by the bifurcations in this paper. Okay. How about bifurcations of codimension 2 umbilic points? Codimension 2 of umbilic points are studied by Ronaldo and Soto. Here, they just classified the generic umbilic points. They didn't study the bifurcations. And personal communication with Ronaldo, Ronaldo informed me that this is work almost finished, where they looked at bifurcations of codimension 2. So here, we don't have the bifurcations, but going to this paper and getting the parametrizations of the surfaces at these points and the equation of the lines of principal curvature and calculating the ideals generated by 2 of those coefficients, we find that the multiplicity of D1, 2 is 1. So here what happened, you have bifurcation of the lines of curvature. The lines will have a structure, topological structure will change, but the umbilic will remain 1. So you have a change from a type of umbilic, but you still have only 1. At this point, you should expect 3 umbilic points when you deform the surface, here 2, 3, and here 2. I hope, Ronaldo, you can check this is true in your calculations. Now, application to singular surfaces, our result also applied to singular surfaces by parameterized by core-rank 1 map germs at the singular point. So we have singular surfaces. If you have a singular surface parameterized by locally by map from R2 to R3, suppose our point is 0, 0. So you want phi of u, phi at the singular point, you want that this set has dimension 1. So this is what means of core-rank 1. So when it's core-rank 1, we call the direction of the one-dimensional tangent space of the surface at the singular point the tangential direction. Now, if the tangential direction is space-like or light-like, it means that if my tangential direction is v, I don't want v to be 0. So I don't want this v to be light-like. So if the tangential direction is time-like or space-like, we can choose a system of coordinates such that this direction is along phi of u, and then E is different from 0. If E is different from 0, then we can compute M of u. Remember, to compute M of u in our conditions, E, F, and G cannot be all 0. One of them has to be non-zero. This is why we impose that our map is of core-rank 1, and that if there is only one direction, it is not light-like. So E is different from 0. An example of these surfaces is the cross-cup. So if I have a cross-cup in R31, and I suppose that P is not, the tangential direction is not light-like, then the multiplicity is 1. So at the cross-cup point, there is only one umbilic point concentrated there. Okay, so there is still, I think, interesting research to do when the core rank is 2 or rank is 0. Where rank is 0, what will happen here? I think the multiplicity will have a contribution from the singularity of the surface. So probably we should get a formula that involves some invariant of the singularity of the surface, as well as when I deform that surface. For example, if I have singularity more degenerate than a cross-cup, I will have cross-cup singularities, but I will have also other umbilic points. So we should get a formula that involves the singularity of the surface as well as the number of umbilics. So I think it's an interesting problem to pursue. Finally, the final topic is to relate the multiplicity of umbilic to the multiplicity of the surface. So what is, let me just then recall here what's a binary differential equation. A binary differential equation is an equation of this form. So at each point on the in the plane, I have 2, 1, or 0 directions. And here A and B are smooth functions in some open neighborhood in R2. Generically, because I have 3 functions here, they don't vanish in general at the same point. We call the discriminant is the set of points where the discriminant of this function is 0. So you have the discriminant here equal to 0. And if it's positive, I have 2 directions. This equation defines 2 directions. Here it defines 1 double direction. And when delta is negative, we have no directions. So the generic configurations of the solution of my equation are in general of this type. This is a folded saddle. This is a folded node and a folded focus. And how do you study these equations? The way they were studied, basically, in the plane, you have 2 directions. You construct a surface where you separate these directions. So you construct a surface where you lift this discriminant here to a curve, and this direction, you separate these directions. So on one side, you have these directions here. This bivalued field will separate to a vector field. So you classify this vector field, but you have to keep in mind that these 2 points project to the same point here, so you have an involution. So basically, you classify vector fields on a surface together with an involution eta. And when the vector field is regular, you get this configuration. But of course, you can have singularities, you can have saddles, and when you have saddles, you project it, you get this folded saddle. When you have a node, you get folded node, and focus, you get folded focus. And these singularities are called folded singularities, okay? The stable folded singularities. In this paper with Bruce, in this paper with Bill 98, we introduced the notion of the multiplicity of the equation. So it counts the number of, the maximum number of folded singularities that can appear when deforming the equation. Okay, and it is given by the codimension of this idea. Okay, and suppose here we have, for example, a star umbilic. Here you have a star umbilic. If I take my surface and I look at the lines of principal curvature, if I deform this surface, and suppose the line of principal curvature have a star, if I deform the surface, the umbilic points is going to be stable. So the multiplicity of the umbilic point is 1. But if I take the equations of the line of curvatures and I deform it, then it will open up and I create 3 folded singularities. So the multiplicity of the equation of the lines of principal curvature is 3. In fact, there is a nice work which is due to Fletcher in his thesis, where he constructed a family of binary differential equation on a surface which deforms the lines of principal curvature to the asymptotic curves. So you have the same surface, you can construct a pair of foliation, a family of pair of foliation. We start from the asymptotic curves until it gets to the lines of principal curvature. And this family, in fact, when you deform the lines of principal curvature, you get these three-fold singularity. So the question arises, what is the relation between the multiplicity at the umbilic and the multiplicity of the equation? And we have a theorem here. If I have P an umbilic point, and suppose that the multiplicity of the umbilic point and the multiplicity of the equation is infinite, then the multiplicity of the equation is always greater or equal to 3 times the multiplicity of then the multiplicity of the equation of the lines of curvature is greater than 3 times the multiplicity of the umbilic points. Do I have time? Do I have a few minutes, Misha? Yeah, well, I think I have a few minutes.
Yes.
Yeah, okay. Okay, I'll give you then an idea of the proof. So the idea of the proof and of the other proofs, basically, to simplify, I take the surface, I take time-like umbilic points, because you have to prove it separately for space-like, time-like, and light-like. So we choose a coordinate system. So you remember at time-like umbilic points, I have 2 light-like directions at each point. So I can choose a coordinate system such that the coordinate curves are exactly light-like curves. So E equal to 0, F equal to G equal to 0. Then F is different from 0. And in this case, the equations of the line of principal curvature has a simple form and has the discriminant of this equation is just the product of L times N. Then if you go to the multiplicity of the equation, according to my paper with Bill, it's given by the multiplicity of this ideal. Now you just substitute B equal to 0 in our case, and this A is N, this C is L, and delta is Ln. So you substitute here and you calculate the derivatives. So you just calculate the multiplicity of this ideal. Well, because I have Ln here, any element here that is multiple of Ln can be simplified. So what is left is Lu squared N cubed and V squared L cubed. And this, I have the multiplicity here is the sum of the multiplicity of L. I just use the properties of multiplicities of ideals or codimension of ideals. This is the multiplicity of L times this, multiplicity of N times this. But here I have L, like this goes. So the multiplicity of this will be just the multiplicity of this one. But I have a cubed here. So the multiplicity is 3 times. So the multiplicity of Lu, for example, N cubed, this is equal to the multiplicity of Lu plus the multiplicity of N cubed, but this is 3, the multiplicity of Ln. So I have 3 from here, Ln. I have 3 from here, Ln, that gives me 6. And the rest, LLU, MMV. So divide by 3, I get 3. This is greater or equal to 0. And this gives me my multiplicity of my equation is greater or equal to the multiplicity of the umbilic point at P. And with this, I finish what I have to say. So thank you for listening. So if you have any questions, please let me know.
Thank you very much, Farid, for this very motivating, I would say, talk.